Okay, let's find the partial derivative of z with respect to x if z depends on x and y according to this equation, yz minus natural log of z equals x plus y plus z to the fourth. You may have seen things like this from Calc 1. It might be a little obscure, but when you find out that one variable depends on other variables, and this is all shown inside an equation, which is usually called an implicit equation, you just need to differentiate both sides of the equation, and there's a lot of places you have to be very careful about things like the chain rule. So we'll differentiate with respect to x, right? So partially differentiate both sides with respect to x. Now, because z depends on x, we need to be sure to apply the chain rule appropriately. And, if we were doing, so because partial derivative with respect to y, sorry, the partial derivative is with respect to x, typo there, treat y like a constant, right? So we're differentiating with respect to x currently. Y should be treated as a constant, so we copy that y. And then z, when you differentiate, if z depends on x, so this should be a dz over dx. And then plus, the just we should complete the product rule business here. So second z times the derivative of the first part, so dy over dx. And we don't have information in the problem whether y depends on x or not. So we just wrote this, and then it'll be up to what happens later in the problem. If we get additional information, maybe if there's no dependence at all, then that would be 0, for instance. But we're not going to worry about that here. We're just going to write this down, and then finally minus the derivative of ln of z, 1 over z, but that'd be with respect to z. So since we need to do this with respect to x, chain rule says we should multiply by a dz over dx. On the other side, things are a little nicer. X differentiates to 1. Y is going to differentiate dy over dx, and then z differentiates dz over dx, and then apply the chain rule to z to the fourth. So we have 4z to the third times dz over dx. Now, again, there's some little details that are kind of we've sort of shoved in the rug a little bit, but we don't know really what the value of dy over dx is, so we'll just keep it. We'll just keep it in here. We were asked to find dz over dx, so let's get all of the since actually now we can make mention of this, right? So since y is regarded as constant, dy over dx equals 0. And so let's replace all the dy over dx's with 0. That's right. Okay, I remember now. It's been a while designing the slides versus recording, but I wanted to just talk through what things look like first without using the fact that the partial derivative is with respect to x. So I didn't want to worry yet too early about treating y like a constant, just to talk in more generalities. But then since y is being treated like a constant, the derivative of y with respect to x is 0. So we just replace some with zeros here. And then let's get all the terms that have dz over dx on one side. That way, here we go. This is how it looks. It looks like a mess in the step above, but if you really kind of pay attention to the algebra details, you should have a thing like this. Now with all the terms that say dz over dx on one side, we can factor that out. And then to really isolate and solve for dz over dx, we can divide both sides by what's in parentheses. Okay, implicit differentiation is certainly kind of a bit of a mess. And so sorry about how this problem type looks, but I think we'll see when we get our chain rule for this type of function, you won't have to worry about this all too much here. Okay, so what about second derivative? Well, remember there's two first derivatives, right? There was a partial with respect to x and a partial with respect to y. So second derivatives are probably going to be messier as well. By the way, if you write f sub x comma y, you actually read these in order. So this really means f sub x. Take that and then find the partial derivative with respect to y. So yeah, if asked f sub xy, find the partial derivative of f sub x with respect to y. And in Leibniz notation, you kind of read backwards. So it's always about what's closest to f. And what's funny is that in the Newton style notation, the little sub x, closest to to f, that x, so with respect to x happens first, and then with respect to y happens second. The way we read the Leibniz notation, this d over dx, for instance, that means derivative of with respect to x, right? So there, again, it's just in how this is read. You got to read backwards in a sense. So there's f. So I'm looking at the middle of this Leibniz notation line. So there's f, and then in front of that there's a d over dx, meaning partial derivative of f with respect to x, and then in front of that, take that result and partial differentiate with respect to y. Okay, so then here's some various notations for f sub yx, written once just with parentheses for clarification of what's going on, and then a couple different Leibniz notations of this. I know this all looks a little funky, but the d squared on top, because if you write them out explicitly, there's two d's on top, two factors of d, so to speak. And f sub xx, so this is nice because you don't have to really worry about the order. But the notation looks a little funky, perhaps. D squared f over dx squared. It's just, these are kind of notations that get used. So look, in the end, there happen to be 4 second partial derivatives. I hope that makes sense and is not too surprising, given that there were 2 first partial derivatives. So let's do some computations, right? So let's take 10x to the third y minus x y to the fourth plus x to the sixth y to the 10th and find f sub xy. Ooh, this y should be tiny. F sub xy of x comma y. So that means find f sub x first. And so we differentiate with respect to x. You get, so treating y as a constant, 30x squared y minus y to the fourth plus 6x to the fifth y to the 10th. And then it's take that, and we're going to take this new result and differentiate that new function with respect to y. So f sub xy, now treating x as a constant, yeah? So we'll have 30x squared minus 4y to the third plus, and then here's where we should probably be a little careful, but x is a constant, so we just copy down the x to the fifth, copy down the sixth for that matter, differentiate y to the 10th to be 10y to the 9th. Okay, it turns out that there's this theorem which says that if your function is continuous, at all points surrounding the point A comma B, then it doesn't matter whether you differentiate first with respect to x and then y or vice versa. But that's so as long as you have a continuous function, this works out nicely. So in other words, take the function above. You ought to, on your own, without using the theorem, just compute what f sub yx is on your own, and you should get the same final answer. And it'll just be an example of Clairaut's theorem.